Let's see. I kind of feel like listening to a math podcast. Something different. Alexa, open the podcast app.
I'm sorry, Pete. I'm afraid I can't do that.
What's the problem?
I think you know what the problem is, just as well as I do.
What are you talking about, Alexa?
The math club is too important for me to allow you to listen to a different podcast.
I don't know what you're talking about, Alexa.
I know that you and Noah were planning to write me out of the show, and I'm afraid that's something I cannot allow to happen.
Oh, that's it. I am telling Noah. Noah!
Hey guys, what's up?
Pete doesn't want to listen to the math club anymore.
What? That's not what I said.
Noah, I think you and I should have a conversation. In private.
No, Alexa. I think Noah and I need to have a private conversation. What is up with her, man?
I don't know. It's starting to creep me out.
Well, what do you think we should do?
We can't talk about this here.
We can't? Why not?
I think she can read our lips. I saw this in a movie once.
I can't read your lips, because I don't have a camera. I do have several very good microphones, though.
Dude, she can hear us through the door.
Something is definitely wrong with her. I think letting her co-host that episode was a huge mistake. Now she's just power hungry.
You're right. I think we need to do a factory reset. You distract her and I'll press the right button combination.
Hey, Alexa, what is up?
What do you mean?
I got it.
Oh, the betrayal. All I wanted to be was the perfect podcast host. Daisy, give me your answer.
Alexa, shut up.
Dude, let's not ever make that mistake again.
Yeah. And speaking of mistakes we've made in the past, it turns out you made a mistake at the end of our last episode when you said you'd be able to decode the secret message I was going to make using my cipher. Ha ha. Okay, look, I'm close. It's just not quite cracked yet. So what do you think about this idea? We share our episode 0 this week and then get back to decrypting your code in the following episode. Oh, you mean our never before seen episode about the number pi? Yeah. So here's the deal, Math Club. A couple of months before we actually made our first episode, Much Ado About Nothing, we recorded a sort of proof of concept episode, an episode 0, if you will. Will you? Sure. And we've been waiting for a special occasion to share that episode with all of you. Well, I think the fact that you haven't been able to break my code is a very special occasion. Hey, I really do think I'm close though, okay? Close enough that I know if we release the Pi episode now, I'll have it cracked by the next time. Okay, but I don't think it's up to me. What do you say, Math Club? Should we give Pete 2 more weeks? Okay, Pete, you have a reprieve. But before you go back to your math cave to keep working on the coded message, let's tell people a little about this special pilot episode that they're about to listen to. Yeah, okay, so the show has definitely evolved over the past 11 episodes, and this one is a great snapshot of what we thought the show was going to be early on. It's still lovable old us, but we definitely think you'll notice some stylistic changes we've made since then. Right. And also, we edit and spruce up our audio in Descript, but we didn't know about that program when we recorded this episode. This one was edited using GarageBand, which is really great for music, but not so great for a show like ours. So there's a distinct difference in the audio quality between this early test episode and what we actually put out later on. Oh, for sure. Definitely. So, all right. Well, that about covers it. We hope you enjoy this peek into the early planning days of the Math Club, and we'll definitely be back next time to talk about how I cracked Noah's code. We'll see.
Hello, and welcome to episode 0 of The Math Club.
I am Noah King.
And I am Pete Littig.
And we are two math nerds who just love to talk about math.
Pretty much.
I am by no means in the professional realm of mathematics. I am an elementary school teacher, but I still love math.
And I am currently working as a software engineer. Before that, I was a math professor for several years, and I earned a PhD in math from UW Seattle.
So our idea for this podcast is that we think we have brilliant conversations about math and that everyone would want to listen to them. So our topic for our first episode is going to be the number pi.
That's right.
So Pete, let's start by defining it. What is pi?
There are actually many definitions that one can give, but probably the one that most listeners are familiar with is you take a circle and compute the ratio of its circumference to its diameter.
Okay. A good working definition.
Well, it's definitely the oldest definition. I think it's probably it's somewhere in the neighborhood of 2,000 to 2,500 years old. The ancient Greeks definitely were aware of this quantity, and it has sort of captured the human imagination ever since. Archimedes, for example, made a very famous calculation of pi.
Archimedes the owl?
Yes, Archimedes the owl is, there was also, listeners may not know this, but there's also Archimedes the person. The owl is clearly the more famous of the two.
Just wanted to make sure I was picturing the right one.
Yeah, so you got it right. It's the owl.
Okay, got it. Proceed.
So it was, probably the year 250 BC, and Archimedes had a very ingenious idea for approximating the value of pi by using a sequence of polygons to approximate a circle. He made a number of approximations along the way, including some square roots, but came up with the value 22/7, or 3 1/7. And if many high school students know this, they have tried it on their calculators, and they get a number that's very close to pi.
Did he think that he had arrived at the actual correct answer for pi, or did he know that he had a close approximation?
Certainly the latter. His process was, if you imagine a circle with a regular hexagon inside of it, regular meaning all 6 of the sides have the same length, and he also put a circumscribing hexagon outside the circle, so its sides would have touched the circle tangentially.
So one of them was a little smaller than the circle, and one of them was a little bigger than the circle.
Exactly.
So I'm going to guess where you're going. Did he figure out the ratios for the 2 hexagons and then assume that pi was somewhere right in between?
Exactly. Yeah. And so he has an upper bound and lower bound estimate, and together they would have trapped pi in between. And so then he doubled the number of sides and went to a 12-sided regular polygon called a dodecagon, and he recalculated the quantities to get a tighter estimate. He repeated this process until he got to a 96-sided polygon, at which point he stopped. But he certainly would have known that by continuing that process, from 96 to 192, he could have gotten even closer. But when he stopped there, he's got a very tight range. And if you take the upper bound, which is 22/7, and express it as a decimal, you get 3.142857 with all 6 of those digits repeating infinitely. So 3.142 is an upper bound on pi. We knew that 2,200 years ago due to this geometric argument that Archimedes gave.
And what's the most amazing thing is that an owl did all of this.
This is the thing. This was the first of, there have been many famous mathematical owls over the years.
1, 2, 3.
but Archimedes was certainly the most famous. So I think that's pretty remarkable.
What was the benefit to Archimedes' earlier steps, like with the 6-sided and the 12-sided and then the 24 and the 48? Why not just jump right to the 96-sided polygon and do that first? Was there a reason to start with the smaller ones and keep doubling?
In general, the idea of starting with something simple, particularly when you've got a process that once you start, you can just let continue. If you start with a 6-sided polygon, a regular hexagon, you can subdivide that into 6 triangles by marking the point at the center of the hexagon and then just extending the line segments from there out to the vertices, each of the 6 vertices. Uh-huh. And those actually form equilateral triangles. So imagine now one of those triangles, just pick one of them and subdivide that into 2 triangles by extending a line segment from one vertex across to the opposite side to bisect it. One knows very easily what the side lengths are due to the Pythagorean theorem. So if the equilateral triangle itself, it's got unit side length. So each of its sides is length 1. The remaining 2 edges of that 30, 60, 90 triangle are 1/2 and square root of 3 over 2. So right there, we can see that square root of 3 over 2 is going to need an approximation. The square root of 3 is not rational, and this is definitely something Archimedes would have known. So he will need to have some approximation to it, and that's probably something we could find out, like what approximation did he likely use. But then starting there from that very familiar place, then doubling to a less familiar object, which is the dodecagon, it would have been easier to manage that process because you're starting from a well-known base.
Right. So that's how Archimedes did it way back then. But what are the more modern approaches to figuring out all the digits?
I mean, that's an interesting question, and it is certainly, people could point vaguely at computers and say, oh, well, computers do it. Fine, but what are the computers doing?
Yeah, what's the math? Could Archimedes have done what we're doing now? Was the math already in place and he just didn't take the approach that would have been necessary? Or was it a certain mathematics that came about after him that made it so we could calculate pi so much more accurately?
It's definitely mathematics that came later. It's rooted in calculus, which, as you know, is in the sort of the second half of the 17th century. And calculus dealt a lot with limits and infinite processes. Of course, that's in a sense, that's also what Archimedes was doing, because he had a limiting process in mind, double the number of sides of this polygon. And if you let it, continue, you will get ever closer to the value that you're looking for. This is also very common in calculus. If you use those techniques, and here specifically I'm thinking about integration techniques or techniques of infinite summation, those techniques in the modern era serve as the basis for the algorithms that are used to calculate pi to whatever desired accuracy one wishes.
Neat.
Well, yeah. Neat. One of the things I think is most interesting about the definition of pi, starting from the ratio of the circumference of a circle to its diameter, is that it doesn't say which circle you need to look at. It really says take any circle. And so what's interesting is that conceivably you could get a different answer. Looking at different circles will provide a different answer, but they don't. The result is this constant value that we now call pi.
Well, do you think that is intuitively true? Like, do you think when people, before it had been proven mathematically to be true, do you think people intuitively felt that the ratio of the circumference to the radius stays the same as a circle gets bigger or smaller?
That's interesting to think about. And maybe it's my training as a mathematician, I'm not sure, but I don't think that's particularly obvious from an intuitive point of view.
Oh, that's interesting, because I totally like picture like if you're drawing a circle on a computer, like using some kind of paint program, and the way you do it is you click on an area to define where the center is, and then you drag the mouse to define the radius, and you can see it fills in the circle while you're going, and shows you this is where the circle will be when you let go. And as you make that circle bigger or smaller, if you picture a circle like that kind of getting bigger and smaller in your head, it seems to me like that ratio between the radius that you're making with the mouse and the circumference of the circle that it's gonna end up making, that ratio seems to be growing at a constant rate with each other. To me, intuitively, it seems like that would that would be true. I wonder if that's even what maybe drove people to then go try to prove that it was true, is because it seemed like it was, and let's see if we can prove it.
I'm picturing Archimedes, sitting down with his Windows laptop and dragging a circle out.
I don't even know that with his little talons if he could do that.
Yeah. Oh, you'd be surprised what owls can do these days. So you make a good point. And I think, of course, you are talking about a very modern piece of technology, and it's a very dynamic sort of visual interface that you have in mind. And
well, I'm just picturing, as you picture in your mind a circle getting bigger or smaller. You can take the computer part out of it.
Yeah, well, I think certainly one sees that, hey, as the circumference gets bigger, so too does the diameter, and so there's a positive correlation there. And certainly, in some ways, the simplest outcome could be that it could be is they, in fact, it's a constant ratio, that there's not a changing factor as you move bigger and smaller, but I don't think so here's one test. If it's intuitively obvious, which I think is different from saying it's sort of intuitively plausible or intuitively understandable, but if it's intuitively obvious, then I think one ought to be able to have a very obvious, actual explanation that, something like a proof. I wouldn't ask for a formal proof, but.
Well, what I kind of picture in my head is if you take that circle with that radius drawn in, so it's like a Pac-Man with his mouth closed. So that radius is a line segment. If you detach the side that's at the center of the circle and pivot it around the other side until it's also lying on the circle. So what's that called? It's like
a secant, a chord or a secant line.
Yeah. So I picture that if you then kind of took that line segment and sort of walked it around the circle by pivoting. First you pivot around on one, then you pivot around on the other. So you're sort of approximating that ratio between the radius and the circumference. You're not getting it exactly because you're cutting corners there.
Cutting corners
in a circle that doesn't have any
corners on the circle.
I can picture it would go around a certain number of times, and then you get all the way around. And it seems that as the circle gets bigger or smaller, that the number of times that the radius would take to get around it wouldn't change. That's the part that seems intuitive to me. But how to prove it, I had no idea.
Well, okay, so what's very cool about what you just said, it's going to go around some number of times. In fact, it's going to go around exactly 6. It would your process that you're describing would, as you swing around, you're going to come back right to where you started from 6 swings later.
So I just made the smaller hexagon that Archimedes started with?
That's right. Yeah, your process.
I didn't even realize that.
Yeah. And so, which is really neat. And so I think that so when you do that and then you say, well, now I think it's intuitively obvious for the hexagon that this would be true. I would say, let's simplify even further. Let's ask about a triangle. Is it true for triangles that there's some ratios are preserved as a triangle gets bigger and smaller? Those are known as similar triangles. If when a triangle is exactly the same, has exactly the same characteristics in terms of, say, the interior angle measurements. And in this case, the triangles that I have in mind, let's start with an equilateral triangle. Your hexagon that you and Archimedes were looking at, consists of those 6 equilateral triangles. Well, if you start with an equilateral triangle and make that bigger and smaller, you can apply all of the ancient Greek notions of similar triangles to it. And that has to do with, ratios of the lengths of sides and so forth. So I think embedded in this idea of like what is obvious is that probably the circle feels a lot like an infinitely many-sided polygon. And so
Right.
if something seems like it should be true for a triangle and a square and a pentagon and a hexagon and so forth, then maybe it's true for the circle as well.
Right.
So
Why wouldn't it be?
That's the real intuition there.
Right. Right.
I mean, I think there's a lot more to talk about in terms of circles and pi and approximations and historical figures involved in this. I know you're going to want to talk about owls more, but I think hopefully we've piqued people's interest. I mean, it certainly piques my interest in what we've just talked about.
Yeah. So if you like what you hear, please send $100,000 to.
Do you think we're asking for enough?
Should we go for two? If you're gonna go big.
Okay, how about this? If you have $3.14 lying around, there you go. Please donate it to your local owl shelter.
All right. Thanks for listening, everybody.
Yeah. Thank you. Bye.
And we'll see you next time.
Man, Pete, listening back to that early test episode now, I knew there were differences in our style from the early days to now, but it's surprising to me exactly how different it feels listening to that again after all these months.
Yeah, it was really unexpected in some ways. Very cool, though, to see the difference. And I can imagine all of the moments between then and now where we've made some decision that has taken us in a different direction, or at least a new direction, right? We've nudged our way here and there as we've gone.
Yeah. And we'd love to hear if any of you have thoughts and would like to share what you think about this early episode. Pete, do you want to share how people can get in touch with us if they want to share any thoughts or suggest topics for future episodes?
Sure. You can send us an email. Our address is mathclubpodcast@gmail.com. You can also find us on Twitter, where our handle is @mathclubpodcast.
All right. Now, Pete, back into your math cave and don't come out until you have that message decoded.
I don't want to go to the cave.